Okay, good morning, everyone. Happy to see you all in the GR seminar. This week we have Dr. Jinhua Wang from Xiamen University to give a talk. The title of his talk is Future Stability of the 1+3 mu model for the Einstein-Klein-Gordon system. Let's leave time to Dr. Jinhua Wang.
Oh, yeah. Yeah. First of all, I would like to thank Liu Jue for this invitation. And actually, the work I'm going to talk today, the future stability of Milne model for Einstein-Klein-Gordon system, it was not a new result. It was result years ago. And the Einstein-Klein-Gordon system takes the following form. These are R bar, and they are rich in scale curvature of an unknown Lorentz metric G bar. And on the right hand side of the Einstein equation is the energy momentum tensor for a massive scalar field. M squared is positive. So the Bianchi identity implies the scalar field satisfies the Klein-Gordon equation. And why Einstein-Klein-Gordon? Actually, this comes from the problem of nonlinear stability of supersymmetry background or supergravity proposed by Professor Yao. And the theory of supergravity comes from the original Karuza-Klein theory. A Karuza-Klein space-time takes the form of the product of the Minkowski with S1. So in this theory, they reduce the 4+1 dimensional Einstein gravity to 4 dimension by compactify the field's dimension on the circle S1. Suppose Z is the coordinate on S1, then the 4+1 dimensional metric is explained as Fourier series. This curly G is the 5-dimensional metric, and capital MN is the 5-dimensional indices. And on the right hand side, the small g n depends only on the 4-dimensional coordinate. So and now consider this 4+1 dimensional vacuum Einstein equation and decompose it into each mode. Well, we will see that the zero mode corresponds to massless field, and physically this is observable. That's the small g0 will reduce to g0 mu nu, the 4-dimensional gravity, and a mu, the Maxwell metric, and the scalar field. So the 5-dimensional Einstein, the 5-dimensional vacuum Einstein equation reduced to 4-dimension Einstein Maxwell massless scalar field, scalar system. And this is supposed to pursue the unification of GR with electromagnetism. But when it comes to the non-zero mode, then the scalar field will be replaced by massive, they will be massive scalar field, and physically this is not observable. And let me explain this by a Toyo model. This is a 5-dimensional wave equation, and it is a Toyo model for a 5-dimensional vacuum Einstein equation. And as before, we do the Fourier expansion for this wave variable. And then this 5-dimensional wave equation will decompose into a series of equation for scalar field. And we see when n is 0, it is a wave equation, massless scalar field. And this equation is scalar invariant. When n is non-zero, this is the Klein-Gordon equation, a massive scalar field. And this equation is not scalar invariant. And now let's talk about the closed Milne model, or in other words, it is the compactified K equals to -1 vacuum FRW space-time. It is a cosmological vacuum space-time taking form of R product with sigma. Sigma is a closed Riemann-manifold admitting an Einstein metric, gamma. So gamma, let's take gamma, the hyperbolic metric with sectional curvature -1. So this n bar and gamma bar is the Milne model, closed Milne model. As we see, it has a Big Bang singularity as t turns to 0, but expand with polynomial growth to infinite volume in the future direction. It was proved by Lars Anderson and Vincent Moncrief. The nonlinear stability of a general 1 plus n-dimensional Milne model. And in this work, in their series of work, they introduced this constant mean curvature spatial harmonic gauge. Highly related to the Milne model is the Minkowski space-time. So let's now review the stability of Minkowski space-time for vacuum Einstein equation. Christodoro and Kreman proved the stability results in 1990s. It was a covariant proof, and the proof relies on the geometric correlations of space-time. Also, the fact Bianchi equation has some null structure, and long time later, the stability of Minkowski was reproved by simplified by Lindblad and Noneski. They used the wave coordinate gauge. And some remarks. This method requires the full symmetries of the Minkowski space-time, including the translation, scaling, rotation, Lorentzian boost, and can be extended to the non-vacuum case with scaling invariant matter fields such as massless scalar field, Maxwell field, and massless Virasov, but they do not apply to Klein-Gordon field or massive Virasov because these are non-scalar invariant. So what's the difficulty of Klein-Gordon field? Klein-Gordon equation is not scalar invariant. So the symmetry of scaling is or rather the vector field S is not allowed, but fortunately it's compatible with the Lorentz boost, which is tangential to the hyperboloid. There were quite a lot of results in the past few years about the nonlinear stability of Minkowski with massive field. the first one is the work of Mayu and the Floch that proved the stability of Minkowski for Einstein-Klein-Gordon system used the hyperbolic method and wave coordinate gauge. And in particular, they use this L infinity to L infinity estimate for Klein-Gordon and wave coordinates. And also there were works on the massive Einstein Villasov and something, maybe there are more updates today. Now let's look at the Milne model. And Anderson and Bachmann, they proved the stability of 1+3 Milne model for this massive Einstein-Villasov system. And now let's consider the Klein-Gordon field. And an additional difficulty of Klein-Gordon field in Milne model is now the partial T is not killing in Milne model, but we know that partial T is killing in Minkowski space-time. So the standard energy norm for Klein-Gordon field will not work in the Milne model. And this is the work that I'm going to talk about today. And I use this CMC with zero shift gauge. And similar result was proved by Bachmann and White using this CMC spatial harmonic gauge. And of course, there are several updates about this kind of massive the stability of Einstein with some kind of massive fields. And let's come to the main results, and I will introduce some basic notations. This coordinate tau x are some local coordinate, and tau is a time function. And here's the definition of lapse and shift. And P is the unit time-like vector field orthogonal to sigma. The zero shift requires x vanish, so that the space-time takes the form of 2.1. And the CMC gauge requires the trace of the second fundamental form to be constant. And in this case, we also require this trace k theta is negative. And for notational convenience, we will turn to a rescale time function P, so that it looks more close to the hyperbole in the Minkowski space-time. And now the corresponding lapse is close one. In terms of T, the second fundamental form is decomposed into the trace-free part and the trace part. And this, the 1+3 Milne model, in this 1+3 Milne model, K, the second fundamental form is trace-free, and now the lapse is identical to 1. And because of this T square, because of this expanding, so we have to do some rescale, and this T bar, yeah, something is more important. T bar is T times the unit time-like vector field, and it is also convenient to introduce the logarithmic time. Tau bar, partial tau bar is scale-free, and after this notations, let's come to the main results. sigma is a compact straight manifold without boundary, and assume G0, K0, phi0, phi1 is a scalar data set for Einstein-Klein-Gordon system. So if the initial data is close to the Milne model, small perturbation of the close to the Milne model, and here we requires the something about the initial Ritz curvature and initial second fundamental form at some small. Then the solution of the Einstein-Klein-Gordon system global exists in the expanding direction, and moreover, during the evolution, the spatial manifold, the Ricci curvature is almost constant sectional curvature, and as t turns to infinity, the section curvature returns to constant as well, and this means it returns to the Milne model as t turns to infinity. Any question or comment now? It's 25. And okay, now let's turn to the proof. We know that there is this two structure, the geometric structure equation. It is a transport equation on the metric G and the second fundamental form. Also the Gauss-Kodály equation and the elliptic for the lapse. So this R bar is the space-time Ritz curvature. And so when the Einstein equation coupled with matter field, this R bar will be given by the matter field. So the full Einstein-Klein-Gordon system in CMC gauge with a zero shift, including this 3.12 evolution equation, 3.2 Gauss-Kodály equation, and the lapse equation. Also the CMC gauge and Klein-Gordon equation. So the local existence is added up to the previous something known, like the maximal gauge with zero shift or the wave coordinate or simply spatial harmonic gauge. And now let's come to the long time stability. The main feature of the proof include the modified energy for the Klein-Gordon field and recast the Klein-Gordon equation in first order form and treat it as a transport equation. And in fact, this is compatible with the energy scheme. That is, we just communicate with the spatial covariant derivative. And our proof is a covariant proof, and this helps to clarify the nonlinear couplings. In other words, we can see some consolations in a coupling structure. And also the hierarchy of energy estimate, including linearization for a borderline term. And this also includes two approaches. The first one is L infinity to L infinity estimate for a Klein-Gordon equation, which was due to Milne and the Flock, and also the refined refined estimate for the lapse. And now let's come to the Einstein part. We use this Bianchi identity. It improves this divergence equation for the wire tensor. Wire tensor is the trace this part of the curvature tensor. Then this J will be related to the Klein-Gordon field, and star is the Hodge-Dual. And for a wire tensor, we do such 1+3 decomposition. So there is the electric and magnetic parts of the wire field E, H. And similarly, this Bianchi equation can be decomposed as the transport equation for E and H. The Beer-Robinson energy is defined in terms of E and H. And for Klein-Gordon equation, similarly, we have do such 1+3 decomposition. And now the 3.8, this is 3.8, we recast this two-order wave equation into a first order form. And so in this form, it helps to derive the higher order Klein-Gordon equation, such as 3.9, because it involves only the commutator between this Lie partial tau bar with Nabla. And for commutator, there's only Nabla, no no scaling, such as or the time direction. And in this high order Klein-Gordon equation, we can see there's such red terms. This is the borderline terms. The arrows are nonlinear terms which are not dangerous, and I just give the definitions here. So now, to do the energy estimate for Klein-Gordon field, the idea is introduce the modified energy for the Klein-Gordon field. As usual, we multiply this 2T bar phi on the Klein-Gordon field, and it will give an energy identity after some integration by parts, actually twice. Then we'll get on the right hand side, this is modified energy, and on the left hand side, this is modified energy, and on the right hand side, there's quadratic term plus E. E is some cubic error term decaying fast enough. Comparing to the standard energy of Klein-Gordon, the modified energy has this extra term. And so we require, if we require this initial time have some lower bound, then this two energy will be equivalent. And as we know, the small data finite time existence is a standard, so we can finally resolve this requirement for the initial time. And in views of the definition of this Klein-Gordon energy, we can see the three term in the first bracket, they are at the same level of regularity, and hence the two terms in the second bracket, they are at the same level of gravity. So it means that if we are allowed to lose one order of derivative, lose some one order regularity, then we can improve decay, gain an extra t-1 decay for tangential derivative. And this idea is used throughout the proof. And now let's look at this quadratic term. So in view of this definition of this of this Klein-Gordon energy, there's this t squared phi squared. So this quadratic term has extra t minus 2 factor, which is integral. So the Green wall inequality works. And for a higher order energy, the definition is given here, and we can see there is no high order derivative with respect to the time direction. Actually, this t bar square phi is not involved in this definition, but it can be estimated through the Klein-Gordon equation. But it is bad. It has growth. It has growth. So this t bar square is bad. Due to this fact, so we have to, in a proof, we have to avoid such t bar square phi to close the energy estimates. And this relies on a key observation. That's a cancellation in the coupling structure, in the couplings of the Bianchi identity. It's exactly 3.15. And as we can see, there's no such t bar square phi in this source term. And as a remark, this cancellation is only needed when taking one more derivative on the Einstein equation, as what we did for the Bianchi equation, but it is not needed if you are considering the original Einstein equation. And in fact, we get this such terms in this coupling structure. Such term, there is a borderline term from the coupling structures. As we know, for the lower order case, as we explained before, for a lower order case, we are allowed to do regularity, so that we can gain additional t minus 1 factor. And so this is good, but this is good. So the energy estimate for the low order case is relatively easier. But for top order case, this approach is not valid. We are not allowed to lose regularity. So in the top order case, this term will provide a borderline term, which requires more work. Besides, there is also borderline terms from the commuting this nabla with the Klein-Gordon equation. It is actually the bracket of nabla with n. It is borderline term because of here is t square. There is t square here. As a remark, if one is considering the massless case, then there's no such borderline term. And for this kind of borderline term, it looks as if one do not multiply this lapse n on the Klein-Gordon equation, then it seems there's no such commutator and no borderline. The fact is, when we are looking at the n multiplied Klein-Gordon equation, it gives the commutator between nabla and d and t over t bar phi. This commutator is good. Correspondingly, there is this borderline term involving the commutator between the nabla and n. And if we are looking at the original Klein-Gordon equation without and multiplied, it gives the commutator between nabla and d t bar over t bar phi. This commutator is bad. It involves t bar square phi, and by using this Klein-Gordon equation, this in turn gives the m squared t squared phi, which is exactly the borderline term given here. So the borderline term do exist in the CMC H. This borderline term has two issues. First of all, it bears the delta loss if we are using this software of embedding due to the weak bootstrap assumption. The bootstrap assumption is given in 3.16. Yes, there's delta loss. But even if there is no delta loss, these are indeed borderline term because of the decay rate is 1 over t, which is non-integrable. And the strategy is using a bootstrap argument. We will close the bootstrap assumption by sharpen this estimate. So for the issue 1, we use this L infinity to infinity estimate for Klein-Gordon field. And this one is an ODE model for Klein-Gordon equation. And we got this estimate of 3.17. This will help to improve the L infinity estimate of T bar phi and T phi, and retrieve the delta loss in the borderline term. But of course, it will cause regularity. There are some remarks on this ODE estimates. In fact, in the textbook of Homander, there is also this kind of ODE estimate for the Klein-Gordon field, but there is no partial S term, but we need it. And this kind of ODE estimate is replaced by the so-called continuity equation in Fachman and Wyatt. The rho is the energy density of the energy momentum tensor, and the continuity equation is the transport equation for this energy density. For issue 2, we observe a linear structure in a borderline term. In this 3.18, this factor nabla a minus 1 t bar phi, or the similar one, they are of low order, which means they are less than L order. And in additionally, this term of lapse, it depends on the lower order energy of the Klein-Gordon field. This can be seen from a refined estimate for the lapse. In this kind of elliptic estimate, we can see the L order energy of the lapse is controlled by the L-2 order of energy of the Klein-Gordon field. Here, this epsilon m t-1 comes from the L infinity to L infinity estimate we have done previously. And so the idea is work together with the hierarchy of energy estimates. The low order energy estimate will sharpen the estimate for this two term mentioned before, and reduce the nonlinear borderline term to a linear one. And this kind of procedure also applies to the borderline terms that arise from in the top order energy estimate for the wire field. And I will explain this hierarchy of energy for the first two order energy estimate. First of all, when for a zero order energy, there's no borderline term. So it's easy to derive an uniform bound for the energy of Klein-Gordon zero order energy of Klein-Gordon field. Here, this I is a constant depending on the data, and this estimate 3.20 will help improve the estimate for the lapse because of the refined estimate for the lapse. And now let's proceed to the first order case where the borderline term take this form. And now we substitute this 3.20 and 3.21 into the estimate. We can see one of the m is replaced by this I is a constant, inverse constant depending on the data. So after Cauchy swatch, we can see here this is a linear term because it involves only one m. And changing to the t function, and using this Grunwald inequality, we can improve the estimate and close the bootstrap assumption. So there's some more remarks. The Beer-Robinson energy method does not depend on the spectral theory on the compact manifolds. So it's promising to treat the case of open mirror. The open mirror means the spatial manifold is now the hyperbole, not the compactified case, and this is working in progress. And finally, let's see more developments on this open problem of nonlinear stability of supergravity or supersymmetry spacetime, including Caruso-Klein spacetime. And earlier, there was this work by Brucha and Moncrief. They are working on the spacetime of R times U1 times two surfaces with genus larger than 1, and they assume the U1 symmetry on this spacetime. And recently, there were two works also assume some symmetry condition. And in fact, for this work, they are considering the zero mode perturbations. The first result with our symmetry assumption was given by Anderson, Brew, Wild, and Yao. They have proved the stability of this 1 plus n Minkowski product with K. K is a compact Ricci flat manifold with some stability condition. In addition, they require this n have to be larger or equal to 9. And myself has also done some work on the small data global existence for the nonlinear wave with arbitrary quadratic terms in the product space time of Milne with S1. This is a toy model for Einstein equation. And recently there was also the work on nonlinear wave is now conditioned in the Minkowski product with S1, and things are still going on. And that's it. And here are some reference. Thank you for your attention.
Okay, thanks for your excellent talk. Any question or remarks?
All right. I guess I would just ask one question.
Hi.
Hi. Yeah. So very nice talk. Yeah. So in this work, you used this zero shift gauge, right?
Yes.
This zero shift gauge. Do you think like any of this analysis, so what is the problem with CMC SH gauge? Like when you don't turn off the shift, like is there a problem? Like I don't know. Like I'm just asking. Like is there a particular problem with the CMC SH gauge, or is it just?
Oh, there's no problem in this project with the CMC gauge, the spatial harmonic gauge.
Right.
And actually, there was proved by Wyatt and Fachman using the CMC gauge with spatial harmonic.
Oh.
Oh, not here. Yes, I have read it. Yeah.
Oh, right. Yeah. I did not see that. I did not see the paper. Yeah. Oh, wow. Okay. But yeah. Thanks. that makes sense. And yeah. And also, do you have any kind of feeling for the the large data problem? Like when I kind of remove the smallness and when I study, for example, not the decay, but like just the global existence, the boundedness of the energy. Is that like any way possible in the Milne setting?
In the Milne setting with lab data.
Yeah.
It seems.
I mean, yeah. Yeah. I mean, I don't think it seems like way more difficult problem, but like.
Because even in the Milne setting, even with Yang Mills,
right,
the small data problem,
right,
I think this is not trivial.
Right. So for the Milne model, even for the small data problem for the Yang Mills, that is still open, right? I guess.
Yeah. This is still open. Yeah, because the Yang Mills equation is itself nonlinear. Itself nonlinear equation.
Right. Thank you. Very nice talk. Thanks.
Okay. Any question or remarks? Okay, if there's no questions, I will stop the